And thanks to everyone for tuning in to our webinar series on fire retardancy. My name is Haskell Beckham, and I'll be serving as your moderator and host today. Before I introduce today's speaker, I'd like to tell you a little bit about the webinar series. So I am assisting the folks at the Industrial Fabrics Association in organizing and planning this webinar series on fire retardancy. This webinar series evolved from member request to the staff at IFAI, as did the topical outline shown on this slide on the left. The plan is to cover the topics in a series of webinars held approximately every 2 months or so. The topical outline and the schedule will continue to evolve based on member and participant feedback and requests. For example, when you registered for this webinar, you were asked to respond to some questions. Your comments will be considered as and taken into consideration as we move through the series. Today we kick off the series with an introductory overview that will be presented by Professor Chuck Wilkie. On October the 27th, Ann Grimaldi of Grimaldi Law Offices and Renee Kalmus of Exponent will cover regulatory requirements related to exposure and toxicology of flame retardants. Future dates and specific topics are to be determined, but as I mentioned before, the tentative plan right now is to schedule a webinar about every 2 months until we get through all of the topics you see there on the left. Let me now introduce our speaker today. Professor Charles Wilkie, or Chuck Wilkie, is Professor Emeritus in the Department of Chemistry at Marquette University. Chuck retired from teaching in 2009 after a distinguished career in teaching and research spanning over 40 years. During his career, Professor Wilkie led research programs on flame retardation and other topics that are described in over 100 publications. He has edited or written 9 books, including Fire Retardancy of Polymeric Materials. He was a Fulbright Hays Scholar and has received awards from the ACS Milwaukee section and Marquette University for excellence in research. Over the years, Professor Wilkie has organized numerous conferences and taught numerous short courses on fire retardancy. Please note that if you have a question during the webinar, please enter it on the GoToWebinar toolbar. We will address the questions at the end of Professor Wilkie's presentation. And now, Chuck, I'm going to turn it over to you.
Okay. Well, I'm happy to be here and talk with you this afternoon about the field of fire retardants. As Haskell said, it's an area in which I have worked for several years, and so it's always fun to be able to talk about that and explain the field of fire retardancy and the complications that are involved in it. So I got to figure out how to work this and advance things. So here's a brief outline of the different kinds of things we're going to talk about today. Basically, we're going to talk about how we evaluate fire retardancy and then how we try to achieve fire retardancy. I'm going to begin by talking about meetings on fire retardancy. And I should say, because I'm saying fire retardancy, and I see here we say flame retardancy. For the most part, we use both fire and flame interchangeably. It doesn't matter whether we talk about fire retardancy or flame retardancy, we're all talking about the same thing. So there are annual meetings. The BCC meeting on fire retardancy is held every May, typically in Stamford, Connecticut. Next year will be the 27th annual meeting. There are European meetings on fire retardancy. They are held every 2 years. There was a meeting held in Berlin this past year, which was the 15th, I believe, and in 2017, the next meeting will be in the UK. There's a Chinese meeting, which is now, say last year was the 3rd meeting. The 4th meeting is coming up then in 2 years, so that'll be in 16. ACS, we do an ACS Fire and Polymer Symposium every 4 years, held at an ACS meeting. That next one will be in Philadelphia. I must mention that there is a short course associated with the BCC meeting. So that BCC meeting will be May 23 to 25, which is Monday to Wednesday next year. On Sunday, the 22nd, we'll have an all-day short course, which will cover everything that I'm going to talk about today and a whole lot more. And of course, there are plenty of other meetings. These are the ones with which I'm involved, and so that's why I'm specifying those here. If you want any additional information on any of these meetings, feel free to contact me. And now I'm trying to make this move again, and it doesn't want to, so okay, now it's working for me. Fire is a very complex subject. We all know that you burn something very easily and you take an organic compound and you end up with CO2 and water. But it's far, far more complicated than that. And on this slide we show the fire triangle or the fire tetrahedron, depending on how we want to look at it. And these show the components that are involved in a fire. First of all, we've got to have a fuel, which is the organic compound that we're all working with now. We've got to have oxygen because ultimately we have to oxidize things to be able to get to CO2 and water. And we've got to have heat because heat is what causes the polymer to break down. We don't burn the solid polymer. Instead, what happens is that solid polymer breaks down, and that will produce small molecules, which are what escape to the gas phase and ultimately burn. The difference between the fire triangle and the fire tetrahedron is we add a fourth component in the tetrahedron, which is chain reaction. And that's what happens when things are going to, as things break down. Flammability tests. Fire consists of starting it, do not let it extinguish. You give off heat. That heat is used to drive further degradation of the polymer. That causes the flame to spread. All of these things go into fire. And every time we do a test, we evaluate one of those. And so that means these small-scale laboratory tests by no means predict how something will behave in a real fire. Instead, they predict how something will behave according to our one evaluative technique. And what that means is when you evaluate the fire retardancy of something, you can't do it just one way. You have to use a variety of different techniques. The ultimate thing is the whole room test, in which you take your material in question, you put it in a room, and you start the room on fire and you see what happens. That's obviously very expensive. And so you try to find out from smaller scale tests what's going to work. There's three small scale tests that I want to talk about here. The first one is Underwriters Laboratory 94. And in that we take, and I should say that there's a vertical test and there's a horizontal test. So I'm going to talk about the vertical test first of all. In the UL 94 test, which is a criteria for selling a fire retardant. So that you want a fire retardant which will give you a V0 or a V2 typically classification in the UL 94, in which case it's allowed to be used much of the time. This is very, very dependent on the thickness of the material. If you start with a very thick material, say something which is 10 millimeters thick, it's going to be very difficult to get it to burn. And you see the way you start it. So you take a burner, a particular burner with a particular size flame, and you hold it for 10 seconds on the end, and then you take it away. And this, you're starting burning from the bottom, and I'll show you in the next slide a picture of what that looks like. But you want to have the material, you want to have the plastic go out. There is a piece of cotton down beneath the flame, or down beneath the piece of plastic that we're interested in. And if something drips from the piece of material and that falls down and it ignites the cotton, that changes the classification. You can't have a classification at all under those conditions. This is a picture of what the test looks like. So you got the cotton down there on the bottom. You put your burner on the bottom of the material, so it's going up, and that's important because that means the heat is rising, or the heat is rising up, and it's going to cause further burning. Something which is burned from the top burns very different than something which is burned from the bottom. This is a pretty stringent test. There's also the horizontal burning. And so for this, your plate piece is going at the horizontal orientation. You started at one end, and that's going to mean it's going to burn differently. That gives a minimum level of fire retardancy. There's also another vertical classification called 5V, which is very difficult to obtain. It's more stringent than the others. Another test that we do is called the oxygen index, or the limiting oxygen index, which measures the minimum concentration of oxygen in a made up for the test oxygen-nitrogen composition. And it measures the minimum amount of oxygen required to sustain combustion. The higher you can drive the oxygen index, the better off you're going to be in terms of fire retardancy. A problem with it is we don't know how high you've got to go because we're measuring only one thing here. This is what the test looks like. So this is candlelight burning. You have your sample inside a glass tube. At the bottom of it, you're feeding in an oxygen-nitrogen supply, and you change the composition of that as you will. And it's candlelight combustion, so you stick your flame down to the top of that piece of plastic and start that burning. This is much, much less sensitive to thickness than the UL94 is. Here's some typical oxygen indices that are obtained for a variety of different polymers. Recognizing that air is about 20% nitrogen, you can see that anything from ABS and above, about the middle of the first column, is going to burn in air very easily. Anything above that is going to require a little more than that. If you get up to the last entry there, it's tetrafluoro or Teflon. That's got a 95% oxygen index, and that's going to be very difficult to burn. One cannot say just what oxygen index is required to have a good system. Some of the time you read in the literature that people say they put in an additive and they drove the oxygen index from 18 to 25. To which I would say, well, you haven't done anything. There's no change. It's not going to change the fire characteristics at all, in all likelihood. I would say, and this is just me speaking, I would say that if you want to have a significant change in oxygen index, you have to change it by at least 10, and 15 or 20 would be better. So that if you can drive your oxygen index up above 40, you probably made some change. If it's not, the likelihood that you really have any kind of fire retardance is slim. This is what happens with glass-filled systems. So it's just more oxygen indices, but now it compares with glass and without glass. And you see, for instance, polycarbonate without glass is 30, polycarbonate with glass is 29.8. There's no change. Polycarbonate with 40% glass is 29.3. So in general, the presence of fiberglass filling doesn't have any influence on the oxygen index. Another technique that's used is the cone calorimeter. The cone calorimeter measures the heat release rate that comes off from a burning polymer. So you take your material, you put it underneath a cone-shaped heater, hence the name cone calorimeter, which is on a load cell. So you're measuring the mass as a function of time. The material starts to burn. Let me start that again. The polymer degrades, and as it degrades, there's a spark igniter in there, which is sparking every second or so into the gases that come off. And so we force ignition. The gases go up. We measure the amount of heat which is given off by measuring the oxygen consumption. And we can also measure the amount of smoke which comes off, and we can measure CO and CO2. This is the some of the peculiarities to the cone. You can set the irradiance to any level between 0, which means no heat, to 100 kilowatts per square meter. Per square meter, the amount of irradiance is going to depend upon the size of the sample. So typically the sample size in the cone calorimeter is 10 centimeter by 10 centimeter. 50 kilowatts per square meter, which is a nice number that's frequently used in the cone calorimeter. 50 kilowatts per square meter corresponds to a temperature of about 600 degrees C. Here's some results from cone calorimetry. And let's just look at the peak heat release rate. And you see for ABS, and this is at 50 kilowatts per square meter, for ABS, the peak heat release rate is 1,000. Fire retarded ABS, it's 414. So we've reduced it by about 60%. That's very nice. For HIPS, you can reduce the peak heat release rate from about 1,000 to 250. So that's about a 75% reduction. But for PCABS, the change from non-fire retarded to fire retarded is much smaller. So you can't say that if we have this size change in heat release rate or peak heat release rate, we're going to have such and such an effect. There are many, many other tests. Usually they involve a whole lot more material. There's something called the ASTM E84, which measures flame spread. And for that, you start off with 24 feet of material, which is 20 inches wide. So that takes a huge amount of material to be able to evaluate that. So those are just a few of the tests that are done. Now I want to look into how we create from the polymer, how we end up producing the fuel, which is what burns. And again, realize that the polymer, the solid polymer itself, does not burn. Instead, we have to cause the polymer to degrade. And the degradation gives small molecules, which are what actually do the burning. There are generally considered to be 4 mechanisms by which polymers degrade. First is random chain scission, which means we can break a bond any place. End chain scission, which means we start from the end of the polymer and depolymerize. Pendant group stripping, which means that's what happens in, for instance, PVC. First of all, the chlorine atom is lost, then an adjacent hydrogen atom is lost to make HCl, and we form a double bond. And then in a rare number of cases, cross-linking occurs. Polyacrylonitrile is the example of the cross-linking mechanism. This shows you the mechanism versus the monomer yield. So So polymethyl methacrylate degrades by chain end stripping. That is, it forms methyl methacrylate monomer. The monomer yield is anywhere from 90 to 98%, and the reason for the variation of that amount is it depends upon initiation. Somehow or other you have to start it. So you can see that in polystyrene, for instance, we only get about 50% of the monomer being produced. The rest of the degradation products are generally going to be higher oligomers of styrene. So a dimer, a trimer, a tetramer, etc. Acrylonitrile goes by cross-linking. Vinyl chloride, vinyl alcohol both go by chain stripping. And again, that means we lose the pendant group, either the chloride or the alcohol, the OH, and then the hydrogen. So we'll form either HCl or water. Decomposition temperatures of various polymers vary all over the map. So that the lowest one there is polymethyl methacrylate, which will begin to degrade, according to this, at about 170. PVC will begin to degrade at about 200, whereas Teflon will begin to degrade at about 500. So the degradation temperature is a variable, and you have to bear that into account when you're looking into which fire retardant you want to use. A definition of fire retardants is that it involves the disruption of the burning process, so the process is terminated within an acceptable period of time or slowed, giving time for evacuation. And the crucial thing here is that you have to be able to escape. Things will burn. You want to be able to have enough time to allow anyone who is in the vicinity of the fire to escape from that fire. Fire retardants must reduce the risk of a fire. If the first thing never burns, then the fire never starts. If ignition does occur, the fire retardants must stop propagation of the flame. And the fire retardant must reduce the spread of flame and the rate of burn. This is a little advertising for why we want fire retardants. This was a study done at NIST probably 25 years ago. They found that if you had a fire retardant product as opposed to a non-fire retardant product, that you had 15-fold longer time to escape from the fire for an FR product. The amount of consumed material was 2 times less. The heat release was about 1/4. The toxic gases released were about 1/3, and we had less smoke come off. So fire retardants have a big advantage. There's lots of ways that we can try to achieve fire retardants. The simplest is to design inherently fire retardant polymers. This is expensive. That's primarily what we expect from NASA for the space shuttle, because there's no way to do it other than that, and you're going to make a small amount of material that's going to be used once. So why not make the highest thermal stability possible? Or we want to modify the polymer in such a way to achieve fire retardants. We can do that perhaps by putting in a comonomer or another fire retardant monomer into the plastic, the material of choice, that's going to impart some fire retardants in. Or we can use additives. Additives are the most common approach, and that's primarily what I'm going to be talking about now. When we use comonomers, what we want to do is have something which is going to degrade differently. Ideally, it's going to form a char. And a char has the advantage of isolating and insulating the surface of the polymer so that we isolate the bulk of the polymer from the fire which is up above it. For additives, there's three basic mechanisms by which we achieve fire retardancy. The first is the gas phase mechanism, in which we generate a material which will quench the fire. This is typically either going to be a halogen or a phosphorus. The second is we put in an additive which is going to cause char formation. And again, char formation is good because it insulates the bulk of the material from the flame above it. And that means that the flame cannot get down there, so it cannot cause further degradation. And if it can't cause further degradation, then there's no material to burn. And the third general mechanism is one in which we use minerals that will endothermically decompose. Typically, these consist of aluminum trihydroxide or magnesium dihydroxide, both of which will decompose to the oxide with the elimination of water, and we'll see later that it's about a joule per gram that this will take on, and so the energy from the fire goes to cause the degradation of the additive, not the degradation of the polymer. Here's one of the beneficial effects of char. If we cause combustion to go all the way to CO2, that's 94 kcals. If we cause combustion to only go to CO, that's 26 kcals. So we've reduced it by a fourth, roughly. And if there's no combustion, then we just have carbon, then we got 0 kcals. So there's a big advantage to having char formation. These are the fire retardant elements. I'm only going to talk about some of them. In order, it's going to be, first of all, we'll talk about halogens, then we'll talk about phosphorus, then we'll talk about aluminum and magnesium. The others are relatively minor players. They have their niches. They are very important in some areas, but the three major categories are halogen, phosphorus, and aluminum and magnesium. A fire is nothing more than the radical recombination reaction of hydroxy radicals and hydrogen atoms. If we can remove those, we've removed the flame. So flame quenching means removing the hydroxy radicals and the hydrogen atoms. A halogen does this very effectively because it will break down, and so our halogen here is Rx, where X is the halogen. That will, first of all, break a carbon halogen bond to make the R radical and the X radical. The halogen radical will react with the polymer to hydrogen abstract, generating the radical from the polymer and HX, and HX is our effective fire retardant. HX will react with the hydroxy radical to make water, regenerating the halogen radical. HX will react with a hydrogen atom to make H2 and regenerate the halogen radical. It's a little counterintuitive to say that H2 is a good thing because we all know H2 burns easily. But H2 is formed and diffuses away rapidly. And so we don't have a problem with it. So this is a catalytic process in which we generate the X atom, the X radical. It will make the HX. It will react to remake the halogen atom, which will then cycle through this, and it will remove all of the hydrogen atoms and hydroxy radicals. Antimony oxide is considered very often to be an effective synergist for halogen. And a synergist means that it improves the efficiency of the material. So that if we simply have a halogen-containing material, we're going to have one efficiency. We're going to have one level of fire retardance. if we put in some antimony oxide, we're going to have an increased level of fire retardants beyond that what you would anticipate from using those two materials separately. There is speculation. This has been studied intensively for a lot of years. This is the best guess as to what happens. So antimony oxide reacts with HCl and ultimately is going to make SbCl3. Or it reacts with HBr and ultimately is going to make SbBr3. Those materials are volatile at 223 degrees or 280 degrees. We've reached the boiling point. And that will help with transport of HX into the gas phase. And so it's believed that this is why antimony is effective. Other synergists have been used. There's iron compounds that have been used. There's zinc borates have been used. Tin compounds have been used as synergists. Antimony oxide is believed has been the best one that anyone has found. So here we're back to what happens with SbX3. Now it will reform the HX, which is our effective fire retardant, so that because of the presence of antimony, we're moving around the halogen atom. And so it is more effective. SbO and SbOH, which are produced in the various processes, can also participate in reactions. M here is any body. Before I move on to phosphorus, I must talk for a little bit about halogens and the problem with halogens. It is widely believed now that halogens are a problem as fire retardants. And they're a problem because under certain conditions of combustion, you can make brominated dioxins and brominated furans. And these are toxic materials. If we end up with these toxic materials, somebody may end up, they're carcinogens, I should say. Somebody may end up achieving or getting cancer from this, and that's not a good thing. It's also known that some of the brominated, decabromo diphenyl oxide is the most common brominated fire retardant. There are also others. There's a pentabromo diphenyl ether, and there's a octabromo diphenyl ether. Those are both known to bioaccumulate. And because of that, they have been taken away. And so those are no longer available at all. DECA has been taken away because there's concern about it. I don't think it's been shown that this happens, but there's concern about it. Right now, the situation is that polymeric bromine compounds are considered to be usable. Non-polymeric bromine compounds are not considered to be usable. And so who knows what's going to happen to bromine in the future? It is one of the most efficient fire retardants that we have. For a lot of different polymers, it is the fire retardant of choice. And that choice is in many ways no longer available to us. The choice of which halogen to use depends to some extent on what the polymer is and what the degradation temperature is of the polymer. You have to be able to generate your HX at a temperature such where you have a flame occurring so that you can quench the flame. If you have something which degrades at a very low temperature, some polymer which degrades at a very low temperature, then you're going to want to have a fire retardant which is available at that temperature. Chlorine is effective and bromine is effective, but bromine is a higher temperature material than is chlorine. Iodine is ineffective because the carbon-iodine bond is too weak. It will break very easily, and you don't have it available when you need it. The carbon-fluorine bond is too strong, and therefore the carbon-fluorine, the HF that you would need is never produced. And I'm not going to talk yet about toxicity, but of course, if you're going to generate HBr and HCl, there is some question as to whether we want to breathe that in. So now let's move on to phosphorus. Phosphorus has become the most common fire retardant element. I would say it has replaced bromine, which used to be far and away the most commonly used material, but now phosphorus is the material of choice, it seems. And some phosphorus compounds function in the vapor phase, some phosphorus compounds function in the condensed phase. So you have some variability and selectivity that you can use with phosphorus. In the vapor phase, that means we're going to quench the hydroxy and hydrogen radicals. In the condensed phase, that means we want to cause char formation. I want to talk, first of all, about a unique form of phosphorus, which is intumescence. Intumescere is a Latin word that means to swell. And an intumescent fire retardant is one that causes the polymer to swell. So an intumescent system usually consists of three components. You have the acid source, which is typically ammonium polyphosphate, which will degrade to give phosphoric acid, which is the acid source. That acid source then will react with the char former, and penerythritol is the most common char former that's used. Penerythritol is simply a polyhydroxy compound. And the phosphoric acid will dehydrate the penerythritol and cause char formation. And then you also have a blowing agent. Melamine is the typical blowing agent that's used, and that will expand the char. And so you end up producing, if you start off with a plaque that's, say, 5 millimeters thick, in an intumescent system, you may well end up with something which is 15 or 20 millimeters thick, so that you really can expand that char a lot by the intumescent system. It's used in polymers, but it is very widely used on steel beams. So that is the protection that is used on the vast majority of steel beams in buildings. And steel beams, the problem with them is if you get up to a temperature of, say, 500 or 600 degrees, the steel loses its integrity and will start to bend. And of course, that means the steel beam is no longer going to hold anything up. So we put an intumescent coating on that steel beam to prevent the steel beam from reaching that kind of temperature. Phosphorus-based fire retardants are effective in oxygen and nitrogen-containing polymers, and now I'm talking about condensed phase materials. They increase the char formation. Polymer will undergo phosphorylation. And the phosphorylated polymers decompose at high temperature to produce char. There's lots of different phosphorus fire retardants. They are very specific for one polymer, so that this polymer can use this phosphorus fire retardant. That polymer, which seems similar, can't use the same phosphorus fire retardant. It's much more effective with a related compound. The char is important because it prevents mass transfer and heat transfer. The important characteristics are how much do we have, how fast is it formed, and what's the quality of the char. If there's cracks in it, it's not going to do any good because the heat is going to go right down through that crack and get down to the polymer. So you must have closed cells that are free from cracks and channels. And if that happens, then you're going to have a nice char which is going to be capable of preventing a fire. We have other condensed phase mechanisms as well. The non-volatile phosphorus species can free radical inhibit the polymer melt. Polyphosphoric acid can coat the surface of the char and prevent its oxidation. Moving on to gas phase phosphorus fire retardants. These have got to function in exactly the same way that the brominated fire retardants do. That is, they have to remove the hydrogen atom and hydroxy radicals. Here are some mechanisms which have been proposed. You can see the reference there. This was work that was done in Russia, and I'm not going to try and pronounce the guy's name who did it, but he did some very, very nice mass spec work in which he looked at the various radicals which are involved and identified what is happening in the system. Now, he was using a model of a phosphorus fire retardant system. So we don't know what's going to happen exactly with other phosphorus-based fire retardants, but with this system, that's what happens. So PO2 is effective. PO2 is effective. HOPO is effective. PO is also believed, the PO radical is also believed to be effective. And those of you who know some phosphorus chemistry know that you never hear about PO. We know about NO. That's a nitric oxide is a well-known material in nitrogen chemistry. It's not well-known in phosphorus chemistry. So these are transient materials that are produced. The combination of, okay, one of the things that people have done for years is to try to devise a phosphorus-based fire retardant or a halogen-based fire retardant or a fire retardant based on this or that. And I believe we're at a time in history when we can no longer think of a single fire retardant as being something which is important for to achieve fire retardancy in a particular polymer, but instead we have to think of a fire retardant system. And so the top line there says that we can have a highly volatile compound and a low volatile compound, and perhaps these are going to be synergistic. We can have inhibition in low temperature flames, that we can, by having char formation, we can help to decrease the flame temperature. In other words, by combining things, we can have a better effect than we have if we don't combine. Moving on to the metal hydroxides. You can see that for aluminum trihydroxide, we're going to get, it's going to require 1 kilojoule per gram to decompose aluminum hydroxide and 1.2 kilojoules per gram to decompose magnesium hydroxide. That means that when these are fire retardants used in a polymer, the heat is going to go to decompose these and not to decompose the polymer. The downside of this is that if all we have is 1 gram, we're going to be able to take on 1.2 kilojoules of heat, and then the rest of it is going to go and get the polymer. So that means we have to put a lot of these in. This is not a catalytic situation. This is a gram per gram situation. And so typically, if you're going to use these as fire retardants, you have to put a lot in. 60% is pretty common. So that you might take ethylene vinyl acetate, which is where this would commonly be used in a heating plenum. And if you take EVA and put in 60% aluminum trihydroxide, you're going to end up with a nicely fire retardant system. But it's no longer like EVA. It's now something which contains an awful lot of the aluminum hydroxide. The second advantage that we have here is that you give off water in this endothermic decomposition, and that dilutes the flame. And so you have water mixed in with whatever it is that's burning, and so that's going to prevent things from burning. These are used for different polymers. This shows you the decomposition temperatures for ATH versus MDH, and you can see that with ATH, aluminum, the degradation occurs at about 300 degrees. That means you have to be able to use the ATH at that temperature. If your polymer is going to degrade at, say, 400 degrees, by the time you get to the temperature the polymer degrades, all the ATH is decomposed, and so there's nothing to be able to take on the heat. So you use magnesium hydroxide with a higher temperature plastic than you use ATH for. There's a whole bunch of other fire retardants, which I'm simply going to mention very briefly here. Borates, which can be used as synergists to help with charring. Melamines, which are used to promote non-flaming dripping. Tin, which is a synergist, helps with charring. Silicates, in the form of nanocomposites, significantly reduce the peak heat release rate and have a positive impact on mechanical properties. There's been an awful lot of work done on nanocomposites. There's also silicones, which can be effective fire retardants as well. The last fire retardant here I want to mention is expandable graphite. This is oxidized graphite, which is made by reacting graphite or stirring graphite basically with sulfuric acid. And that causes sulfuric acid to go between the graphite layers, and you see down at the bottom that you end up with something which the layers are spread out. If you then heat this, something happens, and you end up generating these worms of expandable graphite. And those worms behave in many ways just like an intumescent material. And so we have this expansion that occurs, and this expansion helps us to insulate the material from insulate the polymer from the heat above it. And the volume can increase up to 100 times. So it's a huge volume increase. That's the story of fire retardants. One of the things that everyone's going to be concerned about is toxicity. When you put in an additive, you don't want to generate toxic materials. You don't want to generate corrosive gases. But of course, if you put in a halogen compound, whether it be a chlorine or a bromine compound, you're going to generate some HBr or some HCl, which is not good for them. If you put in a nitrogen-containing polymer, you can generate some HCN. The solution to the problem is to prevent anything from burning in the first place. The biggest tox problem with fires is CO. You can generate a lot of CO, and CO, as we all know, is not good for us. So the best solution to solving any toxic or corrosive gas problem is to stop any evolution of any gases by extinguishing the flame. So you want to have affected fire retardants. You can also use acid scavengers. Magnesium hydroxide, ATH, zinc oxide, zinc borate are affected. You can use condensed phase flame retardants, use non-halogenated flame retardants. All of these things can be affected. So that leads us through where we are with the various fire retardants. And I guess the next thing is for me to respond to questions. So Haskell, where are we going?
Yeah, thank you very much, Chuck. As you've been talking, we have been receiving quite a few questions. Quite a few questions have to do with testing and standards. In fact, the first question that I'll pass on to you is, how do we know what to follow in terms of testing and standards, or which test to proceed with?
The test that you proceed with is the one that you need to be able to utilize your product. And I know that's not an answer. For the vast majority of situations, the UL94 is what is needed to be able to qualify a product for sale. So that if you're a polypropylene manufacturer, you want to have a fire retardant that will give you a UL94 in polypropylene. But if you want to use that on a wall as a wallpaper of some kind, then it's got to pass a wallpaper test. If you want to use it in a plenum for air conditioning or wiring, then it's got to pass that plenum test. So there's tests that are specific to the kinds of material that the kind of application you want to use it
in. Yeah, and I'll just add that specific answers for given markets, in particular markets that are related to industrial fabrics, is one of the topics that we're going to be doing a deeper technical dive in at a future date. But I can see as there are a number of questions in that area, I can see we probably need to do that one sooner rather than later. Chuck, the next question is, what's the difference between a so-called combustible and non-combustible fabric?
Combustible, I think the difference is combustible means it's going to burn, and non-combustible means it's not going to burn. Now, when you throw fabric at me, I can't answer that question because I don't know what the difference is between a combustible and a non-combustible fabric. And I can tell you the difference between something which is combustible and non-combustible, but I don't know.
Okay. Do you think ASTM E84, which I believe you mentioned during your presentation, is an appropriate standard for fabrics? The issue is that with fabrics, it's very difficult to reduce the smoke. Any suggestions?
The problem with the E84 is you've got to take this material and you've got to set 24-foot long material, which is 24 inches wide, up at the top of a column of a furnace and hold it. So I think that's going to be a challenge to hold it in place. As to whether I think it's an appropriate test for a fabric or not, it's the regulatory bodies that determine what's the appropriate test. I can't comment as to whether it's an appropriate test or not. If it's specified, it's got to be done.
All right. Chuck, we have a question about odor and how some of the flame retardant formulations don't smell very good. Any recommendations as to what to do about this? Are there some that simply are known to smell worse than others?
I got to give you my honest answer. I'm not aware of any fire retardant compositions that have an odor associated with them. Most of the time, the fire retardants that I know of are solid materials with no vapor pressure. So I don't know of something which has an odor.
So it sounds like you're saying there shouldn't be an odor then.
That's right.
All right. Here's one that you believe you covered some material around. Is there a synergistic effect between antimony oxide and zinc borate, 50-50 blend?
Synergy is not one of my favorite words. And it's not one of my favorite words because I think it is badly misused. Most of the people in the field, and I include myself in this, most of us are inclined to think that if we put two things together, it has to be synergistic. And we don't have to make any measurements, whatever, to show the synergy. Synergistic really means that you have a better than additive effect, and that means you got to mathematically calculate it to show that you do or do not have synergy. And some of the time, you can put together two things and say it's synergistic, and it's actually antagonistic. In other words, it's not even as good as the additive effect of the two materials alone. So it may well be that some of the time antimony and zinc borate can have synergy in some situations, and it may not be synergistic in other applications. It all depends upon the application that you're dealing with.
Right. There's another question. In the NIST study that you cited, what types of products and test methods were used to assert a 15-fold greater escape route?
The honest answer is I don't remember. I believe it was cone calorimetry, but that's not going to give you, I mean, the only way that could say you're getting a 15 time longer to escape is going to mean if it's a whole room test, and I doubt if it was a whole room test. But so my answer is I don't know. I know this test was done back in the 80s, so it's old.
Another question, is there such a thing as the best flame retardant treatment for indoor and outdoor fabrics?
It's going to depend very critically on what the material is you're dealing with. You can have polymers which are very closely related. For instance, you might take polystyrene and I'm trying to think of what's similar to styrene. Well, all right, so you can take ABS and polystyrene. What's good for one is not necessarily good for the other. So that the fire retardant has to be figured out for each individual system. That's one of the problems that we face, is that you can't say because this worked, that will work. You have to go at each one separately.
Chuck, we have some questions regarding the toxicity issue you brought up toward the end there. We have one of the listeners who is asking about how to reduce the toxicity and still meet CPSIA compliance as well as specific fire retardant compliances. Any suggestions there?
The biggest toxicity problem is CO. And so what that says is you either want to cause it to completely burn to give CO2, and that's going to mean you don't have much of a fire retardant effect, or you want to prevent it from burning at all and end up with just carbon, which means you're going to have excellent fire retardant effect. And those are, I don't know how you achieve them. I don't know how you can go after that.
So Chuck, are you saying the CO is more of a problem in terms of toxicity than some of the halogenated byproducts that you mentioned during your presentation?
Now we're talking about two different kinds of problems. The brominated dioxins are carcinogenic, and so there we're talking about potential carcinogens. CO is just going to kill you directly. So we're talking about a very different kind of situation. I think that the HBr HCl problem is far less important than the CO problem. And of course, you can remove the HCl HBr by simply using non-halogenated fire retardants.
Right. In fact, one of the listeners asked about, is it possible to blend a halogenated fire retardant with one of the phosphate products to deal with its potential toxicity issue?
The trend is towards non-halogenated fire retardants. That seems to be where everybody wants to go. And so if you put in a little bit of halogen, you don't have a non-halogenated fire retardant, and so it's going to be less likely that that's going to be viewed favorably. So yes, you could do it. That's an example of a situation where you want to combine a gas phase material with a condensed phase material, which I think is an excellent strategy for developing a fire retardant system. Okay. But whether it's going to be effective or not, and whether having a little bit of halogen means you cannot claim non-hal, and people want to claim that.
Right. Okay. We have some more questions that I'd like to get to, but before we do that, I just want to stop for a second and point out that we've reached the top of the hour, and if anyone needs to leave, we certainly understand that. But if you're willing to stick around, we're going to go through a few more of these questions. Here's an interesting one, Chuck. The question has, what's the best approach for predicting large-scale fire performance using small-scale lab tests, and can you make that extrapolation?
The simple answer is no. You can, the more small-scale tests you do, the better you can guess as to what the result would be from a whole room test. But you're never going to fully predict. A fire is too complicated. And so when you look at each aspect of the fire individually, you don't look at the coupling between those different aspects. And so you don't really know how it's going to function. So it's hard to make any prediction as to what the large-scale test is going to be like from a single individual test. Again, the more individual small lab tests that you do, the better confident you're going to be as to how well it's going to work.
Right. Chuck, we have a request to explain the difference between durable and non-durable flame retardants.
Okay. A durable fire retardant is not going to wash out. A non-durable fire retardant is going to wash out. So that if you got a fabric and it's going to be washed, you want to have it be durable so that the fire retardant doesn't go away with washing.
And wouldn't those be, Chuck, the ones that are part of the dope before the fibers are spun themselves, or perhaps the ones that are surface treated would be less durable?
Probably. If you want it to be durable, what you really want to do is have it chemically connect to the fiber.
Okay. We're getting lots of specific questions. I'll pass those along to you. But for example, what makes acrylic a difficult fiber for passing fire retardant specifications? Do you have any suggestions specific for acrylic?
No, I don't.
What is the best flame retardant for nylon 6,6?
I don't know.
Okay.
Back coatings have been successful. I don't know what's best. It's going to depend upon the particular application.
Yeah, and again, I'll point out to the listeners that we in the series we're going to have a variety of speakers come in, and some of them will be able to address some of these questions. What about flame retardant or fire retardant best for lowering smoke generation in a flexible PVC?
Well, the problem with smoke in PVC is that you get HCl, which generates unsaturation, which cyclizes to give aromatics, and aromatics burn very smokily. So you want to reduce the amount of aromatics. The question is, how do you accomplish that? If you don't make the olefinic double bonds, then you can never have cyclization, and you're not going to form aromatics, and so you're not going to have smoke. But of course, then you're going to have the carbon-chlorine bond, which has got to do something. So the simple answer is to find a way to not cause aromatics to be formed. The hard answer is, I don't know how to do that.
I was about to say, how do you do that? All right. How about, do you know off the top of your head what would be the best ratio of APP, melamine, and penta?
What would be the best ratio of which?
APP, melamine, and penta.
So you're talking about an intumescent system. The best ratio is a well-known amount. I don't know it offhand.
Yeah.
I think that overall it's probably something like 15, 10, and 5, and I don't know which is which even.
Right.
But it's well known what the correct ratio is to use, and can easily be found in the literature.
Okay. So that's an easy thing to look up.
That's an easy thing to find, yes.
Well, I have a question about bromine. When is bromine going to no longer be available?
There are 3 U.S.-based traditional bromine fire retardant companies. Albemarle, what used to be Great Lakes and is now Chemtura, and what used to be Axo Nobel and is now in the, Israeli Chemical Limited. So I'm going to call that U.S. based because they have a large production facility in this country. All of them deal with bromine. All of them think bromine is going to stay. Bromine as polymeric materials, which are not leachable, is widely considered that it's going to stick around for a long time. I don't know what long time means, but it's considered it'll be around for a long time.
Okay. Is it possible for cotton fabrics to have both fire retardant and water repellent properties without affecting its flame retardant performance?
I
guess the question is, if you have a flame retardant cotton fabric, can you make it water repellent, typically by putting some sort of a finish on the surface, without affecting its flame retardant performance?
I don't know. I'm very keen on the Jamie Grunland approach to fire retardants of fabrics, in which he uses layer by layer approach on them, so that he'll build up a positively charged layer and then a negatively charged layer, and with a few bilayers on the surface of a material, he can end up with excellent physical and fire retardant properties. So I think Jamie has really got a nice system going there, which will be commercialized, I think, at some stage.
Here's a question that's related to the chemistry. How can one overcome the water solubility of phosphated flame retardant products? For example, passing a cone test with phosphated flame retardant becomes a challenge.
In the intumescent world, APP has some water solubility, pentaerythritol has some water solubility, and so that means they can be washed out with time. One of the ways that people handle that is to encapsulate. So you encapsulate the APP, you encapsulate the pentaerythritol with something which is not going to be water soluble. So encapsulation is a strategy that can be used.
Okay. I have a question about plasticizers in the flexible PVC. Are high solvating plasticizers less flammable than lower solvating ones?
I don't know. I don't know much about PVC plasticizers. I know what some of them are. I've used them, but I don't know. I don't know is my answer.
Okay. Does zinc borate reduce smoke as you replace the antimony oxide?
Zinc borate has been used as a synergist. The antimony oxide seems, for the most part, to be more effective.
What's the effect of the shape of the zinc oxide particle, the spherical, antimony oxide? What does the spherical antimony oxide work better than randomly shaped? And does finer antimony oxide work better than work better than coarser material?
There is a so-called nano Sp2O5. It's usually Sp2O3, but Sp2O5 has also been used as a synergist. And I believe there's nano Sp2O5, and that's been shown to be more effective than regular Sp2O5. And I don't understand why that. It makes no sense to me. It seems to me that nano only means that it can be separated down into very small materials, but when you have a bottle of it, it's all going to be agglomerated together, so I don't think it's nano then. But it must be. So I guess the advantage of nano, the advantage of small size, is it's going to be possibly more uniformly distributed.
Okay. Chuck, I believe that's all that we have right now. Thank you very much. I'd like to remind everyone who's still with us. First of all, I'd like to thank our sponsor. Thermetrics provided some sponsorship for this webinar. I'd like to thank Chuck for giving the presentation over the past hour. And I'd like to remind everyone to please mark your calendars for the Industrial Fabrics Association International Exposition, October 6th through the 9th. As part of that, on October 6th, there's going to be an Advanced Textiles Conference. And also, because it's come up a number of times during, Chuck talked about it during the presentation, also during the question and answer period. On October 27th is the next webinar in this series entitled Flame Retardants on the Hot Seat, Controversy Over Health Impacts and Update on State and Federal Regulations. I apologize if we didn't get to every single question, but if you want to follow up with us, we'll try to get to it later. Thanks, everyone, for tuning in, and hopefully you'll come back October the 27th for the next presentation. Thank you.